All right, so just a little bit about the exam. First off, there's 44 total questions and there's the usual 4-hour time limit. And this is like a very cumulative final exam. So about half the exam is new material, meaning the correlation and regression that we've covered in the last 3-ish lessons, I think. And then the other half of the test is review. And it's like really review. I mean, it goes all the way back to the beginning, some of the concepts that we've kind of taken for granted, I guess, then they're going to show up again on the test, like more particularly. So I strongly recommend going back and looking at the past test review lessons, which were lessons 8, 15, and 20, working through all those problems, because those are going to be a little bit more nitty gritty as far as, you know, the specific things that that we learned in each of those different units. And then, of course, you can watch the past test review videos, because we will go over a lot of those every time we have a test review video. So today we're just going to focus on all the new material, and then if you want to review, which I think you should, then you should go back and watch all the other videos. And this test does take a little bit longer, I would say, to take than the other ones have taken on average. Not a whole lot longer. I mean, there's not that many more questions, but just the broad nature of the questions, I think, makes it take just a little bit longer. Like, I don't know, like maybe 20 minutes longer on average, something like that. All right, so now that we're clear at the end of the semester, then we have a huge toolbox full of different statistical methods that we have learned. And so the beginning section of the test, where it's asking you what the best analysis is going to be, then now we have so many different ones to choose from. So we have mu with sigma known, mu with sigma unknown, the paired data test, the independent samples test, 1 proportion, 2 proportions, chi-squared, analysis of variance, and now we've tacked on linear regression down there at the bottom. So really from the last test, there's only that one extra different one, the linear regression down here, but there's just a lot overall. So it can be tricky to kind of keep track of what is what. But basically the same process that we've gone through to kind of decide what method is the right one that we've been using all semester long still works going into this test too. And then of course some of the key things to watch for this sigma known problem. Remember, this one's the easiest one to spot, because somewhere in the problem it's going to say sigma equals whatever, 15 or something. So if somewhere in the problem it's saying sigma equals this, then you know that it's this sigma known, mu with sigma known problem. And if it doesn't say that anywhere in the problem, then you know for sure it's not that one. The paired data test, you just have to, these two are tricky to tell between, I think, the paired data and the independent samples test. Oftentimes they will tell you how they took the differences in the paired data test. So they might say, D equals post-test minus pre-test or something like that. So that can be an indication that it's the paired data versus the independent samples. And then ANOVA, I feel like that one's a little bit easier to spot because we're looking for 3 or more groups in a quantitative variable. And chi-square is, sometimes they use keywords like independence in there, or the key to that one is you have 2 categorical variables and one of them has more than 3 levels there. And then of course regression, the new one here, the different thing about regression versus all of these other ones is that we have 2 quantitative variables. So we're measuring 2 quantitative variables on each individual. So that's different than all of these other ones. And a lot of times the purpose of doing regression is going to be to make predictions. So if the problem's saying, hey, we measured people's height and weight and we want to see if people's height can be used to predict their weight, then that's going to be a regression type problem. So for each of those different methods, then you need to know how to write the hypotheses. You need to know what the specific requirements are for each of those individual tests. And they're all different depending on the test that you're looking at. You need to know how to calculate the test statistic or find the confidence interval, and you need to know how to write the conclusions. And I do feel like on this test, I was looking at it right before this meeting, but in the past, they've kind of given you like a long list of different conclusions and you kind of pick the one that matches. For here on this test, they've kind of changed it a little bit. So you have these drop down boxes where you fill in the right phrase, I guess, to make the sentence true. So I'm not sure if that makes it harder or easier, just different. All right, so let's do some examples, see what we can discern here. So first example, a major study of alternative welfare programs randomly assigned women on welfare to one of two programs called WIN and Options. WIN was the existing program. The new Options program gave more incentives to work. An important question was how much more on the average women in Options earned than those in WIN. All right, so first thing I do is I look at what were we measuring? What was the response variable? And it looks like, in this case, they're looking at how much these women earned. So earnings, is that going to be categorical or quantitative? You can do C or Q. Okay, quantitative, absolutely. So this is a quantitative variable. So then we have to decide if we're looking at one group, two groups, or three or more groups. Perfect, we have two groups. We have the WIN group and the Options group. So once we decide that it's two groups for a quantitative variable, we have to decide if they are independent or whether they're dependent. So if they're dependent, then there was matching or pairing going on. And if they're independent, then the women in the WIN group would be just separate from the women in the Options group. Knowing something about who's in the WIN group doesn't give you any information about who's in the Options group. So the problem reads that they randomly assigned women on welfare to one of two programs. So if you take everybody and just randomly assign them, then that's going to make it independent. So this one is going to be 2 means independent. So remember, if it was dependent, then it wouldn't be a random assignment because we would specifically pair up women that were similar to each other. So, so they would not be randomly assigned to the groups. They would be paired up. Okay, next one. A survey of students in 8 Arizona high schools wished to determine if the smoking habits of students, which has 2 categories, student smokes or student does not smoke, was independent of their parents smoking, which has 3 categories, parents smoke, one parent smokes, or neither parent smokes. So in this case, we basically have 2 variables here. We have smoking habits of students, and we have parents' smoking habits. And both of these variables are categorical. So we have 2 categorical variables, and one of them has 2 categories. The other one has 3 categories. We also have the keyword of independent here. So all of these things would help us point to the chi-square test of independence. I couldn't figure out any hand signals for that one, so. The next one, the ARSMA, I don't know how to say that word, acculturation rating scale for Mexican Americans test was compared with a similar test, the bicultural inventory, by administering both tests to 22 Mexican Americans. Researchers wanted to know whether the population mean scores for the 2 tests are the same. All right, so this one, it looks like we're measuring the scores on these tests. And is scores categorical or quantitative? Quantitative. And we have quantitative, and are we looking at one group or 2 groups? 2 groups, right? We have these 2 tests, the ARSMA and the BI test. So we have 2 groups. So we have to decide if the groups are independent or dependent. So in this case, they say that both tests are given to the 22 Mexican Americans, meaning that the people in the ARSMA group are the same exact people who are in the BI group, because each person got both tests there. So because each person got both tests, then they are dependent. Knowing who was in the ARSMA group tells you exactly who was in the BI group. All right, because elderly people may have difficulty standing to have their heights measured, a study was done to see if height to the knee could be used to estimate a person's overall height. So in this case, we're measuring a couple things here. We're measuring height to the knee, and we're measuring overall height. So both of these variables are quantitative. So we have two quantitative variables. And anytime we have two quantitative variables that we're looking at, remember two variables measured on the same individual, then we're dealing with regression. So some other keywords we could use to help us figure out that this was regression. We wanted to see if height to the knee could be used to estimate a person's overall height. So we're using one variable to predict or estimate the other variable. All right, suppose there are 3 routes you can take to work and you're interested in determining which is the fastest. Each day you randomly choose a route to take and measure the time it takes to get there. After 30 days, you analyze the data. All right, so what we're measuring is the time that it takes to get to work, which is what kind of variable? Quantitative. So we have a quantitative variable. Some of you guys, I can only see like the very tip tops of your heads, which is fine. You don't have to show me your whole face. I'm just seeing like a little hair patch on the top. Okay, so it's a quantitative variable, and how many groups are we looking at? How many different routes were we comparing? 3, comparing the 3 different routes. So if we have a quantitative variable and 3 or more groups, then we have ANOVA. All right, next one. When a police officer responds to a call for help in a case of spousal abuse, what should the officer do? A randomized controlled experiment in Charlotte, North Carolina studied 3 possible responses to spousal abuse: advise and possibly separate the couple, issue a citation to the offender, and arrest the offender. The effectiveness of the 3 responses was determined by whether or not the subject was rearrested. Okay, so here we're measuring 2 things here. We're measuring like the response to the spousal abuse, which had 3 different options. And we're also measuring whether or not the subject was rearrested, which had 2 options. So both of these are categorical variables. So when we're measuring 2 categorical variables on the individual, and one of those categorical variables has 3 or more levels, which this one does, then that leads us to chi-squared. All right, a noted psychic was tested for ESP. The psychic was presented with 200 cards face down and asked to determine if the card was one of 5 symbols: a star, a cross, a circle, a square, or 3 wavy lines. The psychic was correct in 50 cases. You wish to see if there's evidence that the psychic is doing better than just guessing. That is, if the percentage of correct guesses is better than 1 in 5 or 20%. All right, so basically what we're measuring here is whether or not the psychic was correct. So he had 20 cards, and he's going to try and guess what's on the card, and if he guesses it right, then he got it correct, and if he guesses it wrong, he gets it wrong. So what kind of variable is that? Is that categorical or quantitative? Right, we have categorical.
Oh.
So we're looking at a categorical variable because we're just looking at right or wrong kind of thing. And then the other thing that helps us know it's categorical is we're interested in these percentage. So we want to know if the percent is better than 20%. So then we have to look at whether we measured one group or. So if we look at the data that was collected, we had these 200 cards, but they were all shown to the same psychic, right? So we're comparing our one sample with the one psychic to a fixed value of 20%. So that makes this categorical, one group. So that's going to make it one proportion, analysis for one proportion. All right, so kind of in general, and this is the same slide I've had in previous test review videos, but when you're thinking about writing the hypotheses, remember that the null hypothesis is always going to have the equal sign in it, and the alternative hypothesis is either going to be greater than, less than, or not equals to. And read the problem for the context clues to figure out what the alternative hypothesis should be. And this is going to apply to regression also, where we're testing that slope. The beta equals 0 versus beta can either be greater than, less than, or not equal to 0. So the exceptions to this rule for writing your hypotheses are going to be analysis of variance and chi-square. So in ANOVA, our null hypothesis is that all the means are equal, and the alternative is that at least one mean is different. And then in chi-square, we have variable 1 and variable 2 are independent versus the alternative that variable 1 and variable 2 are not independent. When we're looking at hypothesis tests, if the p-value is low, then HO must go. So if p-value is less than alpha, then we reject. So if we reject the null hypothesis, that means that we have sufficient evidence that the alternative is true. And if we fail to reject the hypothesis, that means we have insufficient evidence that the alternative is true. So just like on the other test, like I recommend if they're asking you a question about a conclusion, just writing out the conclusion before you write down what, or look for the correct answer, because that usually helps you get less confused because there's a lot of options sometimes. When we're thinking about confidence intervals, and I felt like there was a couple of good confidence interval questions on the review, because I did get a few emails about some of those questions. So the way that we write our confidence interval conclusion is we are whatever % confident that the true mean, and fill this in with whatever it is that you're estimating. So it could be the true proportion, it could be the true difference in the proportions, it could be the true slope of the regression line. So whatever it is that you're trying to estimate, that's what you put in here. And then you say is between the lower bound and the upper bound. So watch out for words like chance and probability, especially if they're used in conjunction with actual numbers, because that's going to make them wrong. And watch out for statements about individuals or other sample means. And I think these were the ones that kind of threw people off on the test review lesson that you guys did in your groups yesterday. This bottom one here is one that always throws people to, and that's because this is based on a method that produces confidence intervals that contain the true mean, whatever C is, % of the time, then it is correct to say that 95% of all 95% confidence intervals will contain the true mean. So this is just something that's generally true about confidence intervals and is not a specific conclusion about a particular data set. All right, so let's talk about the new material that we've been looking at. So first off, now that we're dealing with two variables, both quantitative variables that are measured on the same individual, then we give them special names so we can distinguish between the two variables. So we call one the response variable and one the explanatory variable. So the response variable is going to be our Y variable, sometimes called the dependent variable, and it's what you're trying to predict or what you're trying to estimate. So sometimes it makes sense because if there's some kind of time order to how you collect your data, then the response variable will be like the output, it'll be the end. So for example, like I used to work at 3M, and you might know 3M because they make Scotch tape and Post-it notes, and but they actually make like so much stuff. I had no idea until I worked there. They make like everything. Like almost everything you buy has something from 3M, some little part in it that's made by 3M. One thing they make is the reflective sheeting that goes on stop signs or your license plate or the crossing guard's little outfit with the reflective gray thingies on there, or even your Nike swoosh that's reflective. Like all that stuff comes from 3M. So there's a plant that was near me that I would go to when I worked for them, and one of the things that we were interested in at that plant was how shiny was the shiny stuff. And so the shiny stuff is all produced in like these big roll processes. So it kind of is like a wrapping paper roll, like at Christmas time, like your wrapping paper roll unrolling, like it unrolls and then it goes down this conveyor belt, and the whole way through it's going through ovens and they're throwing things on it like different chemicals and things, and then at the end you have your shiny stuff. So we're often looking at what kind of things influenced how shiny the shiny stuff was. So we look at temperature and the pressure and how fast the line was moving and the amount of chemicals that we were throwing on this thing. So in this case, you can see that there's a definite like time order, like what comes first in the line is the temperature or the line speed. Like those are all things that I can physically turn the knob on, I can adjust. And then when I get to the end, my end result is the material, and I can test how shiny that is. So in that case, the shininess is the response variable. It's the end result. And it's easy to find in that situation because, like I said, there's a time order to it. So the other variable is called the explanatory variable, and this is what you're trying to use to make your prediction. So in my 3M scenario, then the line speed or the temperature or the pressure or the amount of the chemicals that we're putting on there, all of those things would be explanatory variables. So they kind of come first. So it's really nice when it has a time order because I feel like it's easy to figure out what the response and explanatory are. If they don't have a time order, like let's say we're just looking at height and weight, well, in that case, it's a little bit more difficult to figure out, which comes first, your height or your weight. They're kind of both just there together. So in that case, then you have to really look close at what it is that you're trying to predict. Are you trying to predict height using weight, or are you trying to predict weight using height? And you have to read the problem to figure out, okay, what is it that I'm trying to predict? If you can figure out what you're trying to predict, that's your Y, and then the other variable is going to be your X. So here's a couple of examples. The first one says, the Columbus Zoo conducts a study to determine whether a household's income can be used to predict the amount of money the household will give to the zoo's annual fund drive. All right, so in this case, the two variables we're looking at are household income and the amount of money given to the annual fund drive. So let's look at household income. So do you think a household income is going to be X, the explanatory variable, or Y, the response variable? So maybe you can make like, I don't know, hold up an X with your hand if you think it's an X, or what would be a good Y? Look, do Y, like, BYU, go Cougars. Okay, yes, so X is the household income, and then that would mean that Y is going to be the amount of money given. And the way that we can tell this is that it says that we want to predict the amount of money given to the fund drive. So whatever we're trying to predict, that's going to be our Y. And then it says household income was going to be used to make that prediction. So whatever we're using to make the prediction is going to be our X. Okay, here's another one. The height in feet and volume of usable lumber in cubic feet of 32 cherry trees are measured by a researcher. The goal is to determine if volume of usable lumber can be predicted from the height of the tree. So the two things that we're measuring here are volume of usable lumber and height of the tree. Okay, so let's look at volume of usable lumber. Do you think that that is going to be X, the explanatory variable, or Y, the response variable? Okay, good job. This one always throws people, but not you guys. You guys are, it's not early enough in the morning to confuse you. Okay, so so volume is going to be our Y, and height is going to be the X. This one does have a little bit of a time order, like you probably would look at the height of the tree, how tall it is before you chop it down and be like, hey, I wonder how much lumber that's going to make. Then you chop down the tree, I guess. But the wording here is what really helps us. So it says the goal is to determine if volume of usable lumber can be predicted from the height of the tree. So again, we're trying to predict the usable lumber from, or in other words, using the height of the tree. So whatever we're predicting is Y, whatever we're using to predict is going to be our X. All right, so we have our X and our Y, and we're ready to start analyzing some data. The very first thing that we always do with our data is graph it. We're going to describe it graphically. And the type of graph that we use for two quantitative variables is called a scatter plot. And there's basically three things that we look for on the scatter plot. We're going to look for form, direction, and strength. And form, we just want to know, is it linear or nonlinear? And basically we want to know that because we know what to do with linear relationships. We can do regression on those, but in our class we don't learn how to do anything with nonlinear ones. So we're really like kind of crossing our fingers that it's linear. Then we have direction, positive or negative. If it's positive, then as X increases, Y also increases. So if I look at, for me, the temperature outside and my electric bill, they have a positive relationship. So as the average temperature for the month goes up, then so does my electric bill, because my air conditioning bills, I live in Texas, so air conditioning bills go out the roof during the summer when it's really hot here. And then if I think about a negative relationship, well, the temperature outside and my natural gas bill have a negative relationship. So the warmer it gets, then my natural gas bill goes down because I have natural gas heating. So when the temperature outside is low, then my gas bill goes up. So they have an opposite effect on each other. And then strength is just how close do the points fit the form, and specifically that line. So if you're thinking about the fat hot dog test that was talked about in the book, like, are we talking about a really fat hot dog? Are we talking about like a turkey dog, you know, on the skinny side? Are we talking about a Costco hot dog with a whole bun on it? Like how fat is your hot dog? So once we've looked at a scatter plot, the next step is to look at a numerical summary of the relationship. And we use correlation for that. So correlation is denoted by the little lowercase r, and it measures the strength of the linear relationship between X and Y. So it takes values between -1 and +1. Values that are close to -1 have a strong negative relationship. Values that are close to +1 have a strong positive relationship, and values that are close to 0 indicate weak or no linear relationship. So if you think about the absolute value of R, then the closer you are to 1, the stronger it is. And then the sign on R really just indicates whether the relationship is positive or negative. So for correlation, when we talk about correlation in statistics, then we are only talking about relationships between quantitative variables. And this is something that usually throws a lot of students off, because you probably hear the word correlation thrown around a lot, like in the news or things like that. And they might say things like, oh, you know, the relationship between, or there's a correlation between gender and income, and men make more money than women. Well, that kind of correlation that's not how we define correlation in statistics. And if you look at how you calculate correlation, you guys never have to calculate it by hand, but it's this big, ugly, messy formula. And there's no way to plug in a categorical variable. So when we're talking about correlation, both variables have to be quantitative. So if you were looking at like a list of statements about correlation, for example, and trying to pick out the ones that might have errors in them, be vigilant about looking to see if the variables that they're looking at are quantitative, because I feel like that one throws people off more than other ones. And correlation is highly affected by outliers, which is why we always want to do a scatter plot first, because that's going to help us see whether or not there are outliers. Okay, so here's 5 different values for R, and we're going to see if we can match those to the scatter plots that I have down below. So we're going to really test out our sign language skills here. Let's start with the first one, 0.030. So do your best to make your hand look like the letter that you think goes with the scatter plot that goes with 0.030. So A, B, C, D, or E. Okay, I'm not sure if I'm reading everybody's hand signals right, but the correct answer is D. Is that what you guys were saying? Okay, perfect. Okay, so D is the answer to this one. Why? Well, look how close this is to 0. This is really close to 0, which would indicate that there is pretty much no linear relationship between X and Y. And if you look at D down here, like those points are just all over the place. It's like a, you know, like a blizzard or a snowstorm. If you were going to draw a line through there, like you could draw any old line and it would be just as good as any other line. So D is the one that has close to 0 there. Okay, next one, 0.915. Which one is that one going to go to? Okay, awesome. So 0.9, maybe I should be writing these on here. I'll write this one on here, 0.030. So C is the correct answer for this one, 0.915. Okay, and one thing you tell about this correlation is that it's positive. So that means that on a scatter plot, the points are going to go from the lower left to the upper right, like they do here. And it's a pretty strong relationship because it's close to 1, so those points should fall pretty close to the line. Okay, so so that was C. Okay, so the next one, 0.735, which one does that one go to? All right, oh, good idea, holding up the paper to the screen, that works. Okay, so B, yes, B is the correct answer for this one. So this one's also positive, just like this one, but if you're trying to decide between which graph would go with which one, because they're both positive, you can see that the difference between C and B here is that B is a little bit more of a Costco hot dog and C is a little bit more of a turkey dog over here. So the closer to 1, the more turkey dog it's going to look, and the farther away from 1, the more Costco hot dog it's going to look. So this one's 0.735. All right, so looking at these last two, we only have 2 left and two numbers here. Notice that they're both negative. So because they're both negative, then the direction of the relationship is going to be the opposite of what we've seen with the positive one. So it's going to go from upper left to lower right, and you can see that as one variable increases, the other variable decreases. So let's do this first one, negative 0.544. Do you think that that one is A or E? A, perfect. So negative 0.544, and that means that this other one is negative 0.939. Okay, so here's another question. This one's a little bit harder. Okay, which, I don't know how we're gonna, I'll ask for the graph number. So look at the graph letter that corresponds it. So which one of these correlations here is the strongest? Do you think it's the A, B, C, D, or E? So look at the number that goes with the graph to help you figure it out. All right, so the correct answer, and this is a tricky one, is E, okay? So remember when you're looking for the strongest that you actually have to look at kind of the absolute value of the numbers. So I saw a couple people put C, and this is people's tendency is to choose the positive one that's closest to 1. But remember that if you're closer to -1, like this one is, then that actually makes it a little bit stronger of a relationship. So when you're looking for which one's the strongest, you look at the absolute value, whichever one's the greater with absolute value. All right, so once we decide that there is a linear relationship, we do have a correlation, then we like to do a linear regression model. And this is what our linear regression model looks like. It's y hat is equal to b naught plus b1 times x. So y hat is just the predicted value for y. B naught is going to be our y-intercept. So it would be the value for y if x is equal to 0. So as a number, oftentimes the y-intercept isn't that interesting to interpret. But the part of our model that we love the most, and is the most interesting, is going to be our slope. So the slope is a rate of change, and it tells you, it actually quantifies that relationship between x and y. So it tells you for every 1 unit increase in x, you're going to expect y to change by whatever the slope is. So if we're talking about height and weight, and our slope was 5, then it would say, okay, for every 1 inch increase in height, we would expect weight to go up by 5 pounds or something like that. So it's a very specific quantification of the relationship between X and Y. And then of course, X is just our explanatory variable in that model. So suppose we want to see if a person's height can be predicted from their arm span. And we collect data on 25 college students. So height was measured from the top of the head down to your toes, just like normal. And the arm span was measured across the back from fingertip to fingertip. So the first thing that you want to do is do a graph of the data. We want to do one of those scatter plots. So we get the data all entered in here. And if we look back here, it says, suppose we want to see if a person's height can be predicted from their arm span. So person's height, is that going to be X or Y? Yeah, perfect. So person's height is going to be Y, and then their arm span is going to be X. So it says person's height is being predicted, okay, and it's being predicted from their arm span. So what we're using to predict is the X, and what we're predicting is the Y. So here's the data entered into our Excel spreadsheet here, the X and the Y value, and when we do that, then we get the lovely scatter plot over here down in the corner. So if I blow that up, here's what it looks like. And we're looking for 3 things on this scatter plot. We're looking for form, direction, and strength. So first of all, form, we basically want to know, is it linear or not linear? And again, you can kind of do that fat hot dog test. Or if you don't have a hot dog handy, you really can just take your pen or pencil and kind of squint and hold it up to the computer screen. So if I close one eye and hold my pen up to the computer a little bit far away, then I can cover up almost all of those points in a straight line on my computer screen. So that would indicate that it is linear. The direction is going to be positive in this case, because you can see that as somebody's arm span increased, so did their height. And that kind of makes logical sense with what we would expect. And the strength, again, how far away do you have to move that pen from the computer screen, or how big is the hot dog you'd have to use to cover up those points? And these, when you look at it, it very clearly looks like a line. So this is a pretty strong relationship between arm span and height. Okay, so next step is we're gonna look at correlation. And again, this is just in our spreadsheet over here in Excel. It gives us that model summary. So this is just that model summary all blown up. And R is our correlation. So we can see the correlation is 0.898. And again, the closer you are to +1 or -1, the stronger the relationship. So an R of 0.898, that's pretty strong. That indicates a strong relationship. All right, the next step is to model the data using regression. So in, again, our Excel output, then we're given the values for B naught and B1. So they're over here in our coefficients table. So the top number is going to be the intercept, and the bottom number is going to be the slope. So we can create our regression equation using those numbers. So I just plop those in right down here to create my regression equation. So basically what this, how we'd interpret these numbers, the 20.054, that says if your height is 0, or sorry, if your arm span is 0, then we would expect you to have a height of 20 inches. So kind of doesn't really make sense in an interpretation kind of way. That's why the intercept is more like the ugly stepchild, and our favorite child is always the slope, because it's the most interesting one and the one that actually has application every time. Since we probably don't know very many people with a 0 arm span. But the slope here, that 0.707, what that says is for every 1 inch increase in arm span, we expect height to increase by 0.7 inches. All right, so one thing that we can do with our regression model is make predictions. So to make predictions, really what we're doing here is we're taking the X value that we're interested in. So in this case, we want to predict the height for a student whose arm span is 65 inches. So we're going to take that 65 and just plug it in for X and solve for Y hat. That's how we make predictions using our model. Now, of course, we can do this in Excel and have Excel do it for us. So in Excel, and here I'll back up to the whole, here's the big screen. Down here at the bottom, this is where we're entering in the value that we want to predict. So I would enter it into this little bluish grayish box here. So entering 65 into that little box, then it gives me the predicted value here. So this is what we would predict when the arm span is 65. And you could verify that just by actually plugging in 65 to the equation here and making sure that you get that answer out. Now, the next thing we want to know is we want to start doing statistical inference on our model. So if we want to know, is arm span useful for predicting height? Well, we can look at the slope, at doing a test on the slope. Because if the slope of your line is, or if your line has a slope, really, then that would indicate that we would, X would be useful for predicting Y, that there is a correlation between X and Y. So they're all kind of interrelated to each other. The slope, the correlation, and whether or not there's a relationship, or in other words, whether or not one variable is useful for predicting another, they're all tied together. So the way that we test this is a test on the slope, and this is how we write the hypotheses. So the hypotheses are written, the parameter is called beta 1, okay, and then the estimate for beta 1 is the B1. So this is very similar to when we wanted to predict mu, then we used X bar. And when we want to predict sigma, then we use S. And when we want to predict P, then we use P hat. And now we want to predict beta 1, and so we're going to use B1. So B1 is the statistic, and beta 1 is the parameter. So null hypothesis, beta 1 equals 0 versus the alternative hypothesis, beta 1 not equal to 0. And Excel does this test for you. The trickiest part is just remembering where to get the test statistic and p-value from. So in Excel, it does test for both the intercept and the slope. But remember intercept? Remember that was the ugly stepchild that we didn't like? Well, I mean, we like it. We have to keep it around because we just do. But it's not the most interesting one. So pretty much, except for getting this value here to make your model, you can ignore everything else about the intercept. Because, like I said, ugly stepchild, right? So the part in the output that you want to focus on is the part about the slope. So in this case, to do this test, our test statistic is going to be that 9.778, and the p-value then is going to be really, really, really close to 0. So we interpret this the same way we've interpreted all of our other significance tests that we've been doing all semester. So in this case, P is low, it's really close to 0, so HO must go. So we'd reject the null hypothesis, and we would conclude that the slope is different from 0. And based on the data in our sample here, we can see that our slope was positive. So we can conclude that there is a positive relationship between height and arm span. So there's a couple of things that we can look at one of the goals of regression is to make predictions. So we might want to know, hey, well, is our model actually good at making predictions? And one of the things that we look at to help us figure out if our model is any good at making predictions is a measurement called R-squared. So R-squared measures the percent of the variation in the response that can be explained by the model. So if you think about height and weight. So knowing somebody's height can tell you some information about how much they weigh. Like in general, taller people are going to weigh more. But if you think about some of your friends, let's say you have 3 friends that are all 65 inches tall. Are those 3 friends going to weigh the same exact amount? No, of course not, right? Well, why not? I mean, we said height was useful for predicting weight, but those 3 friends are not going to weigh the same amount. Well, height is not the only thing that would determine somebody's weight. It's kind of part of it, like it helps, but it's not the whole thing. There's other factors that might influence somebody's weight, like genetics, or what gender they are, or how active they are, and what kind of diet they follow, and all these other things. So if we kind of want to know, okay, well, if I'm thinking about this like a pie chart, sort of, like what slice of the pie would represent the person's height in terms of how much it affects their weight, and what slice, what would be left over to be everything else that might influence somebody's weight. And that is what R squared measures. It says, okay, what percent of all that variation that we're seeing in weight is explained by somebody's height, and how much is left over to be explained by everything else, all those other things we mentioned, plus whatever we didn't think of to mention. So that's what's measured by R squared. Now we calculate R squared by taking R, which is the correlation, and just squaring it. Like, it's a very simple calculation. But it's important to remember that what they measure, correlation and R squared, they measure different things. So so it'd be a good idea to just kind of, think about this definition for R squared, and then think about what you know about correlation, and think about them kind of separately from each other, even though we do use one to calculate the other. So once we've squared R, it takes values between 0 and 1, or 0% and 100%. So the closer you are to 100%, the better your model is going to be at making predictions, because your X variable explains so much more of the variation that you're seeing. So in this case, our R squared was 0.80, or in other words, 80.6%. So we're saying that 80-ish% of the variation that we see in overall height can be explained by somebody's arm span. So this actually says, hey, our model is okay. It does an okay job of making predictions. It's not going to be perfect, because it's not 100%, but it's going to be at least a pretty decent ballpark figure. The other thing that we look at to help us figure out if our model's good, and also to help us check the requirements for regression, are going to be the residuals. So residuals are the leftover variation, and we can calculate a residual for every point in our data set. So we calculate residuals just by taking the observed Y, so the actual Y that we measured, and subtracting the predicted Y, which is what our model would have said that we should have gotten for Y. So Y minus Y hat. So if our residual was equal to 2.5, that would mean that the observed value, so the value we actually got, was 2.5 units higher than what we expected, or what our model would have predicted. And if the residual is negative 2.5, that means that the observed value is 2.5 units lower than what we expected. And I think there was a good question on the test review about residuals, kind of getting at the definition of the residual and what a residual meant. And so there might be something kind of like that on the exam too. So in Excel, then once you enter in your data, it automatically calculates the residuals for you. So they're in a little column there. And then we can use those residuals. We usually like to look at a graph of the residuals, a couple different graphs of the residuals actually, in order to figure out whether or not we've met the requirements for regression. So here's the 5 requirements for regression. So regression is definitely the toughest one to figure out, hey, do we meet the requirements for this test? So we have these 5 different requirements, and you can see the chart of how you check each of these. Now, I would definitely write this chart down somewhere on your cheat sheet. And I'd probably just write it down verbatim, even if you think you remember things, just because I feel like sometimes it's helpful to like recheck the wording of these things when you're in a situation where you're faced with like multiple choice questions that might seem very similar, or things like that, or check all that apply kind of options, things like that. So the first requirement is that we have a linear relationship between X and Y, and we can tell if it's linear just by looking at the scatter plot. So if we have a hot dog shape in our scatter plot, then we have a linear relationship. We could also look at the residual plot, and as long as there's no residual pattern in the residuals, then that will help us out. And I'll talk in a minute just about how to do the residual plot. We want to see if the error term is normal, so we do a QQ plot of the residuals. So to do that one, I can't remember if I made a slide specifically about this, but you just actually copy and paste the residuals into the first Excel sheet that we used back in the beginning of the year that has the QQ plot tab on it. So you're going to paste the residuals right into there to look at a QQ plot of the residuals. And remember, when you're pasting, to right click and paste just the values. Otherwise, it had a formula in the original Excel sheet to get the residual in the first place. So you want to make sure you're pasting the values in there so it actually gives you real numbers. So we're going to also check for constant variance using the residual plot as well. So basically, we're looking to see if there's any kind of shape in the residuals in the residual plot, and that indicates two of these things: constant variance or whether or not it's a linear relationship. So these last two, we can't measure them directly. So the x's are known constants. We don't have a graph or anything to check for that. We hope that the x's are measured accurately and precisely, but again, there's not really any way for you to check that, and you cannot check that on these graphs. And then the observations, it being independent, you can't check that with any of these graphs or any calculations or things like that. You could read the problem and see how they collected their data. Basically, you don't want them to be taking repeat measurements on the same individual, because that makes the observations not independent anymore. So these are the three key things that can be checked by you using the three plots here: the scatter plot, residual plot, and QQ plot. And we'll look at what we're looking at on those. Okay, so first of all, like again, here's the residuals. They're in Excel. And the first thing I'm going to show you how to do is make sure you get that residual plot. So what we're doing a residual plot of is the residuals versus the explanatory variable. So versus the X variable right here. And they made it easy for you in the Excel sheet, because once you enter in all the data over here, you get both of these two together. Just make sure you don't get confused between whether you do the plot with the X variable or the Y variable. If you forget, look back at the Excel sheet and see which one they're putting together with the residuals here, which is the X variable. So then in Excel, you can just go to Insert and then choose Charts here, and you're going to choose a scatter plot in the charts. And then it'll just put the, did I put it? I'm trying to see if oh shoot.